So we had a lot of talks today about large language models, right? LLMs were the hot topic. Eric started it out. Then we had Korn talk about the foundations of large language models, and Vaibhav spoke about the model garden. So I am here to talk about how we can actually leverage these LLMs in an enterprise context, or how we can make use of these large language models, not only for searching and querying information, but on top of our own personal data, right? But in a more of an enterprise-wide context. Okay. All right, so I'm Thiru. I lead the artificial intelligence division of Root Code called Root Code AI. And today we'll be looking at how we at Root Code solved a massive problem one of our enterprise customers had with using large language models, and how that can potentially be a very useful strategy to work with LLMs in the long run. And if you have any questions, you can scan the QR and drop it by. We can discuss it at the end of the talk. Yep, we'll give some time for that. All right. Okay, so let's start with the model. Because before understanding how we can use large language models in an enterprise context, it's important to understand how these models train and work, right? That's the foundation of how we can leverage these models to the maximum. So this is, for example, GPT's training pipeline. It's a pretty complicated diagram directly from OpenAI. So we can dissect it down a little bit. So like we saw in the previous talk, the first step of training any LLM, any large language model, is basically next word prediction, right? You feed the large language model massive chunks of text from the internet, and you simply ask it to predict the next word. So in this case, you have a Shakespeare text, you ask it to predict the next word, and at initialization, when you first run the model, it doesn't work really well, it just puts out random characters. What you do then is you train the model to use the previous words to predict the next word. This is called self-supervised learning. This is a method to effectively use data openly available on the internet to train large language models, because we can't put human effort into labeling these data. Moreover, represented by this. So it uses the previously laid out words to predict the next word. And over time, as this model trains, over hundreds of iterations, you can see that it convincingly understands meaning of language itself, right? Over 250 iterations, it's trying something, but when it comes to 5,000, it's pretty good in generating poetry. So that's the foundations of large language models themselves. So what these models develop is a foundational understanding of language itself. And that stops there. So how do we get from there to models which can understand conversations, right? How do we get to ChatGPT and Bard? We have to simply train this model once again to follow instructions, because every conversation we have with ChatGPT or Bard are simply instructions we give the model. So this is called supervised fine-tuning. This is the second stage of an LLM training pipeline, where you use a supervised approach. Simply, you have prompt and response pairs, and you ask the model to, you give the prompt and you ask it to generate the response. And this is a very supervised training process. So prompts are like the inputs, and the response is like the, oops. Okay, it's back. A talk isn't a talk without a technical issue, so. All right. So we have a response, and like we spoke, it's a very supervised approach where we train the model to follow instructions. So what do we get after this massive volume of training over terabytes of data? We get this. We get a model that's powerful enough to help you prepare the night before a talk. And we also get a model that's also powerful enough to, generate comebacks. Trust me, it comes in really handy. Okay. But there is something very interesting happening here too. Not only, so we all have used ChatGPT and Bard, right? You know, to search for information, to query answers. It feels more like searching the internet in a more intuitive way. But something even more interesting these models can do is that they can even answer questions which they are not trained on, basically. So in ML, we call this in-context learning. So for example, we have a question here. It says, you know, it's a simple prompt. John is 22 years old and Sarah is 8 years. Sarah has an 8-year age gap with him. When, you know, John was 10 and Sarah was 2. Is she the elder sister or younger sister? Very, very simple concept. But this foundation is what powers us to use these LLMs in real-world production contexts. So the LLM answers the age gap between Sarah and John is 8 years. Simple, right? But what has happened here is we didn't ask the LLM to go look into its previous history of knowledge to generate the answers. We are basically asking the LLM to use the prompt provided itself to generate the answer, right? And this is a pretty powerful concept, so let's keep this in mind. And before we jump into our use case, there is a staggering difference between LLMs and chatbots. LLMs are the models themselves, so we have models like Palm, GPT-4, and Claude, you know, which these are the foundational models, these are the large language models. And tools like Bard and ChatGPT are wrappers around these models which provide a conversational UI. So okay, all of us have seen, you know, all of us have used ChatGPT, so nothing interesting about what we spoke until now. So what's the story here? So at Root Code, we work across a range of industries to build AI solutions. We work with fitness enterprises, to United Nations, to even some European governments, right? So recently, one of our automobile customers came to us asking us, you know, they had an interesting problem. So just to give some background context, this is a 112-year-old European manufacturing giant. And they produce the electromagnetic components from escalators to cars, automobiles, right? So safe to say they are a major part of the entire automobile supply chain. The problem they had was, whenever they get a new project, whenever they get a project to, you know, manufacture a new type of sensor or manufacture a new type of you know, electromagnetic braking system, they had this massive process until development, right? So first it starts with the project managers, they draft out the product pipeline, then it goes with the design team, they design the product, they do the fabrication, and then it goes to the factories. So all of this happens, and in each and every step of this process, there's a massive volume of documents generated. And being a company which is more than a century old, they had more than 1 million of these documents at their fingertips, or at their storage. So the problem here comes in when a project manager, someone starting a new project, wants to go and check back at some of those previous projects they've done to, you know, to, for example, not make the same mistakes they did in the previous project. And that was extremely hard, because trying to search through project files was a mess, right? So they had millions of documents. How are you going to search through it? So although they had this wealth of knowledge in their, you know, within the organization, they were not able to use it properly. So first question, so they came to us and they wanted to build a conversational layer on top of these data, right? So that simply, you know, similar to talking to ChatGPT or Bard, the internal staff or the decision makers at this company can talk to their data, or more like a Bard or ChatGPT for their internal data. So first approach is, why not train an LLM, right? Simple as it is. You know, most LLMs have a training API. I think Palm is still on release on inference only, but OpenAI has a training API, and they have listed the benefits. There's higher quality results. There's ability to train on more examples, and so on. And the training pipeline is pretty straightforward too. You just create prompt completion pairs, which are, in our case, question-answer pairs. We have to create questions and answers, right? Simple as it is. So, but what are the disadvantages of training? Why shouldn't we go for that approach? First is data privacy, right? In our case, the data we were working with was extremely sensitive data. So this was, files and designs of automobile vehicles which weren't even released yet. So that was a problem there. So there was a massive data privacy issue there. And training an LLM is way more expensive than simply using the inference API. And of course, final problem being, it's not scalable when there are new documents being added in the future. We can't simply just go ahead and keep training whenever they add new documents, right? It's not gonna work out. And it takes a lot of manual effort to create the data set. I mean, who's gonna look at documents and create question-answer pairs? It doesn't work well that way. So the second option is, it connects back to what we spoke earlier, using in-context learning or using prompt-based learning, where we don't update the weights of the model directly, but indirectly what we try to do is we try to use prompts to make the model retrieve and extract information from our documents. So in a general context, we have the question, and we have the context document. For example, it's a progress update document here about a specific type of car. And the question we are asking is, the user is asking, for example, what specific advancements have been made in the integration of lightweight materials? So we have the question, we have the document. Why don't we simply combine them together and pass it to an LLM, and we get the answer? And for this demo purposes, I use BARD. Again, this is a fictional document. And it worked out pretty well, right? It does answer the questions really well. But problem comes in, what if we have multiple documents? We were speaking about searching across multiple documents, right? We can't simply, concatenate all these documents into a massive list and then just pass it to the LLM. That's not gonna work out. And most of these LLMs have something called a context length. A context length is basically the maximum volume of text you can pass into an LLM at any given time. For example, for Palm, it's 32K, Palm 2. For GPT-4 also, the maximum is 32K. So anything more than 32,000 tokens of text, the API is gonna reject it. So not the best idea too. So if we simply break this problem down, one is we need an efficient way to extract context related to the question. Right? That's problem number one. Problem two, we need an optimal search strategy here. We need to make sure that we search through these millions of documents in an efficient and effective way. Third, simple but very important, the answers should be accurate. So how do we go about this, right? So if we just simply start from scratch, the first step we take is we do something called document slicing. We segment the document into meaningful context chunks, right? So we take these documents and we use models like UniLM or other simpler large language model to extract meaningful parts of these documents and store them separately. So here, we have 3 different paragraphs, so we split them as 3 different contexts. And then we have something called the document embedding module. Embedding is a very simple concept. I think we had one of the speakers speak about it in the first talks too. But what we do is, we take these 3 contexts, we push them into an embedding model, and it spits out a bunch of numbers. An embedding is basically just a numerical representation of the text itself. So we have 3 input contexts, we have 3 matrices. So what is an embedding, right? Embeddings, like we spoke, are just numerical representations of the text. And what a numerical representation allows us to do is that it allows us to project this text on a 2D grid, right? So that now it's in the form of numbers. Texts which are closer to each other will be closer together. So for example, document context or document pieces which are closer to each other will be closer together. And what we do is we embed we take the embedding of the question also, and then we project it into this 2D space. And what we get there is when we project the question, we can see which context documents are closest to the question. So at this point, it's kind of like nearest neighbors. We project the embedding of the question, and we try to find which document context match it. So now instead of searching through millions of documents, we try to filter out specific contexts which actually make sense to the question the user is asking. And if we look at this overall training pipeline, we have the documents first. So we have a document embedding pipeline. First, we get the documents and we slice the documents. Then we have a document embedding module where we push these documents in and we get their numerical representations. And then we store these documents in a vector database. A vector database is simply a specialized type of database used to store vectors, numerical representations, and that can perform vector search very effectively. And then we also have something called a question embedding pipeline, right? So we have the question, we pass it through an embedding model like OpenAI embedding or PaLM2 embedding. And then we have a vector search module which will query the vector DB and try to find the closest context to the particular question. And then we pass this both to synthesize a prompt or to create a prompt, which would then be passed to the large language model. So again, pipeline, we pass through the user question into the embedding API, get the numerical representation, and then we try to extract the most relevant question, context for that particular question. And so that is overall gist of the solution. But what's the tech stack we use? It can be looked from 3 different perspectives, right? We have data storage on one end. We have to connect to these data sources which contain these documents. Then we have the model. We have large language models like GPT and PaLM and Claude and all that stuff. And we also have the vector DB. So these are the 3 main components. For integrating all these together, we use LangChain. That's a framework we primarily use, but there are also proprietary frameworks like Cohere, and Hugging Face. For vector DB, current industry standard is FAIS. It's Facebook AI Similarity Search. That's the current standard. And we have Pinecone and Milvus, which are proprietary vector DBs. We also, and for models, we have GPT-4 and PaLM2, which are currently the standard, but we also have Claude from Anthropic, which is in closed user testing. So first problem is solved. We needed an efficient way to extract context related to the question. Okay. Second problem is also solved. We needed an optimal search strategy done. But we had a third problem here, that the answer should be accurate, right? And as powerful as LLMs are, they do not always generate the most accurate answers, because they are not designed in a way to generate answers accurately. This is where the concept of system prompts come in, right? System prompts are pieces of text or prompt instructions that you pass in with every query or every API call, which defines how the model should behave when it's generating the answers. For example, in our use case, we ask the model to only answer the question based on the documents available. So don't get too creative and spin up things. Just use the documents as reference and answer the question. But let's say you're building a customer support chatbot or a customer sales chatbot. Then you can ask the model to be a helpful customer support assistant. So there are different ways to do this. And depending on your use case, you can craft how you want your model to behave. And this will set the standard for how it's generating the answers. But it's not always easy using LLMs, right? So hallucination, what just we spoke about, is just one of the issues. So even Bard sometimes generates misinformation or generates things out of context. Very common. No current large language model is immune to this, but they are all rapidly improving. Second is when building solutions using large language models, we need to think about how we can solve the costs and inference time issues. Because generally, large language models take a bit more time than general API calls to generate answers, right? So if you are leaving a synchronous API call from your application to the LLM, you are definitely at the possibility of facing timeout issues. So general practice, best practice is to keep this asynchronous. Second is cost, right? You don't want your customers to see a $20,000 bill at the end of the day. So you need to make sure that and you're charged for also the size of text you feed into the LLM. So you need to make sure you make it as efficient as possible and pack in as much context into the LLM to generate your answer. And an important fact when working with LLMs is, although we have easy access to these models, the data strategy is as important as your model, right? How are you going to make sure you extract this context and store them in the right way? And if you have different types of data sources, let's say you may have structured data, like database tables, then you may have unstructured data, like PDF documents and review documents. Each of these documents have to be handled separately. And your pre-processing pipeline should be able to handle these documents separately. So that's a major concern to think about. And when working in enterprise use cases, it's always almost important to think about how you can integrate this all in one place, right? Because definitely we cannot host our own LLMs. There is a whole discussion about open source versus proprietary models, but current proprietary models outperform all open source LLMs available. So Vertex AI is a solution from Google, and recently they released the Model Garden, which I think Vaibhav also covered, but I can go through that a little bit. So they have this concept of a model garden where you can try out with Palm. It's in closed user testing, so if you can apply as a student, I think you can get it. And there are a few interesting things happening. One is you can directly give in a context, ask a question, and get an answer. But there are also a few parameters you can see there. So the temperature decides how creative the model should be. And in ML terms, we call this stochasticity, right? We try to see how random the model can be. And the higher the temperature, the more creative the model would be. So in general use cases, like when working with enterprise, when we're building models to refer enterprise documents, we keep the temperature to near 0 so that it doesn't, we keep it nearly to 0 so that it doesn't spit out misinformation. And there is also models, there's also a product called Enterprise Search, which was released very recently by Google, so that it's a packaged version of whatever we just spoke about. It's an end-to-end tool where you can directly connect your data sources through GCP and then let it answer questions. So in conclusion, large language models are extremely powerful tools, but having the LLM itself isn't enough. You need to make sure how you store the data, how you vectorize the data. That's one area to think about, how you connect with your data sources, and also how you make sure that your data is secure and private, right? When working with sensitive information, you need to make sure that the LLM providers do not store your data so that you don't want your customers' personal data to end up in ChatGPT or Bard when someone's randomly querying. All right, okay then. Thank you, everyone. Yes. All right, thank you.
Thank you, Thirunayan, for that valuable session. To give away the token of appreciation, I would like to invite Tharaka Devinda, former community organizer for Google Developer Group Sri Lanka.